to the power of n and Pn of x. Okay. So here, what we will do is, in order to get this our proof, so we'll substitute minus x in place of x in this equation 1 minus 2xz plus z square whole to the power of minus half, which is equals to summation of n is equals to 0 to infinite and z power n Pn of x. So there we'll take this equation. Okay. And in this, we have been substituted in place of x. We have written minus x. See here. Here we have 1 minute. I'll take this one. So here, in place of x, so we have written minus x. This one is the equation we have. Then again, one more thing what we have to do is, again, in place of z, we have to substitute minus z in the previous equation. So therefore, here we'll get 1 plus 2xz plus z square whole to the power minus half should equals to 1 minute.
Hello, sir, voice or not there, sir?
Yeah. Now it's okay, no?
Yes, sir. Yes, sir.
Okay. So we have substituted in place of x minus x, we have substituted, and as well as in the equation 2, whichever we have seen previously. So there we have substituted in place of z minus z, we have substituted, so that we have got this equation. So this is the equation. Summation of n is equals to 0 to infinite and minus z whole to the power of n, Pn of minus x. Okay. Therefore, this equation, we can write it as in this form, that is summation of n is equal to 0 to infinite minus 1 whole to the power of n and z power n, Pn of x, we can substitute here. This is the equation. So this is the equation which we have substituted minus x. This is the equation in which we have substituted minus z. Now what we'll do is, we will compare these two equations 4 and 5. So one we have written minus x, one we have written minus z. So if you compare these two, so here you see, we are going to get this one, that is summation of n0 to infinite z power n Pn of minus x. This is the equation 4 we have. And here we have equation 5. This one, summation of n is equal to 0 to infinite minus 1 whole to the power of n z to the power of n Pn of x. So this we are taking it as equation 6. Now simply we are what we call comparing the coefficients of z power n, we are comparing. So on the LHS, if you take the coefficient of z power n, we have like Pn of minus x. This one we have, that is what we have written here. And in the RHS, the coefficient of z power n is minus 1 whole to the power of n and Pn of x. This one we have. So that is what we have written. So therefore, this is the equation Pn of minus x is equals to minus 1 whole to the power of n Pn of x. Right. Now here, if we take condition like that, if you put n is equals to 2m, which we call it as even in equation 7, and here in place of n, what we have written, p of 2m minus of x is equals to minus 1 whole to the power of 2m, and p2 of p2m of x. Okay, so this one we can write it as a p2m of minus x, which is equal to p2m of x. We have, right? So now if we take another condition, that is n is equal to 2m plus 1, this can get it as odd. So therefore, here in this place only we substitute in place of n, we substitute 2m plus 1 in order to get this as odd. So finally, we'll get this equation as this one. Okay. So this is the equation which we are going to get, p of 2m plus 1 minus of x is equals to this one. This is the equation which we are going to get. Okay. And another equation which we have is means the same, we can write it as a p2m plus 1 of minus x is equals to minus p2m plus 1 of x, because so therefore we have got this equation. Now we will substitute x is equals to 1 in both sides. So that we'll get this Pn of minus 1. Okay. Pn of minus 1 is equal to minus 1 whole to the power of n, which is Pn of 1 is equal to minus 1 whole to the power of n, because Pn of 1 is 1. Okay, so this is the equation which we required. So this is problem we have. So we have got this equation 8, 9, 10, whichever we will observe, if you observe. So Pn of x,
Why is not there, sir?
wait for 1 minute.
Okay, sir.
Okay, so this, sorry for the interruption. So here if you take these equations 8, 9, 10, we can say that Pn of x is an even function of x. And for even and odd functions, for n is equal to 2m, we call it as even function. For n is equal to 2m plus 1, we have called it as odd function. So we have got this equation. This is one problem which we have to prove. Okay, so we go through that one, and then we'll start actually the Rodrigues formula for Legendre's polynomial. This is important one. So this will solve it. Okay. So the Rodrigues formula for Legendre polynomials is given by this equation. Okay. So this is the Rodrigues formula we have. That is Pn of x is equals to 1 by 2 power n factorial d power n by dx power n x square minus 1 whole to the power of n. Okay. So this is a Rodrigues formula. This we have to get it. So for that purpose, we will consider this y is equal to this one. This is one we are going to consider. Y is equal to x square minus 1 whole to the power of n. So as we have solved in the case of the Legendre's differential equation, so here also what we are do is we will differentiate this equation once, then after twice. So if you differentiate equation 1 once, that we are going to get it as a dy by dx. So you know that x to the power of n differentiation is nx to the power of n minus 1. So it will be n. X is here x square minus 1, and n minus 1 we are going to get. And again, if you differentiate this, x square differentiation is 2x, and you are going to get this equation 2. So this is the dy by dx we have got. Now what we'll do is we will be multiplying both sides to the above equation by x square minus 1. Okay. So here on LHS we are multiplying here with x square minus 1. So it will be dy by dx, x square minus 1 into dy by dx, and RHS also we are going to multiply with this x square minus 1. So here if you multiply with x square minus 1, so here already we have x square minus 1 whole to the power of n minus 1. So you are going to get it as x square minus 1, you are going to x square minus 1 whole to the power of n you are going to get. Already we have multiplied with x square minus 1. So this remaining 2nx we are going to write. So now we can write this x square minus 1 into dy by dx is equals to as this, that is 2nx. And you know that x square minus 1 whole to the power of n is y we have assumed. So we will take this as a y. Then again, what we'll do is differentiating this equation here, n plus 1 times by using this theorem. We call it as a Leibniz theorem. So we'll get this in terms of this one we are going to get. So n plus 1 times if we differentiate. Okay. So this is a Leibniz, you have to remember this Leibniz theorem. So then we are going to get it as x square minus 1 in place of this dy by dx. If you differentiating n plus 1 times, you are going to get it as a d power n plus 2 y by dx power n plus 2, and plus we are doing n plus 1 times. So here n plus 1 c1. Here we have n c1 no. So in here we are differentiating this equation n plus 1 times. So we are getting it as n plus 1 C1 into d power n plus 1 y by dx power n plus 1 to x. And next, similarly, we'll get n plus 1 C2 and this value d power n y by dx power n into 2. Okay. So which will be equals to this and the RHS whichever we have here 2nxy. So that we are multiplying with the n plus, we are differentiating n plus 1 times. Okay. So we'll get this one. So that is 2n into this value we are going to get. So now what we'll do is we'll rearrange. That is, we are going to take this right hand side terms whichever we have will take into left hand side and we'll equate to 0. This equation we are going to get. So here you see this equation we have written as this x square minus 1 whole to the power of dn plus 2 y by dx power n plus 2. And here if you take these two LHS, we are going to get this equation. So finally we are getting it as here you see, which is equals to 0. So if you rearrange this entire equation, here this equation, entire this equation, if you rearrange, we are going to get it as equals to 0, right? So again, we can finalize this equation as equals to this equation 4. So that is, we'll be rewriting this equation. Once again, we are rewriting, we'll get this one. So after getting this equation, we have to substitute the value of d power n by dx power n as phi of x. We have to substitute. So therefore, here we have differentiated n plus 1 times so that we have got n plus 2 of y. So in place of this, that is d power n y by dx power n is equals to phi x, we are going to substitute. So therefore, here we have we are going to substitute. We getting it as a d square phi by dx square. And minus this one, we will getting it as a d phi by dx, and this one, this third term n into n plus 1 into this d power n y by dx power n, we are taking it as a phi. So that phi we are going to get right is equals to 0. So this equation, whichever we have, this equation, Legendre's equation, which will be having the solution. Okay, so this is the equation we have. So solution is this one, phi is equals to d power n y by dx power n. So this we can write as this one. Okay. So hence we may relate this solution phi of x with Legendre's polynomial. Legendre's polynomial is Pn of x. As Pn of x is equal to phi of x, we can write. Okay. So and before this phi of x, we'll write a constant c here. So Pn of x is equals to some constant into phi of x. So this one, as we have taken it, y value is equal to this one, x square minus 1 whole to the power of n is equal to this total value we have taken, x minus 1 whole to the power of n into x plus 1 whole to the power of n. So now we will differentiate this by using the Leibniz theorem again n times. So this equation we are going to get n times. Previously we have did for n plus 1 times. So now we are doing n times. N times we are doing. So this will be d power n y by dx power n. So by following the Leibniz theorem, as I have written brackets, I'll share these notes. You go to this one. So Leibniz theorem, whichever we have, basing upon this theorem, we are differentiating n times, and we are going to get this entire equation we are going to get here. Okay, this is the equation we are going to get here. Now, after getting this equation, so this by expanding with the help of Leibniz theorem, so we'll put x is equals to 1 in this equation. Okay. So if you put x is equals to 1 in this equation on both sides, so here on the LHS we have d power n y by dx power n, and x is equals to 1 we are going to be taken. And here if you put x is equals to 1, this term will be becomes 0, this term will become 0, and almost you are going to get this one. Okay, only last term whichever we have here, you see d power n by, here I have written d power n into x minus 1 whole to the power of n by dx power n is equals to, you are going to remain. So that one here last term whichever we have. Okay, so that d power n by dx power 1 and x minus 1 whole to the power of n, this one it is going to be, this term it is going to be remains. The entire other equations is going to be get equals to 0, because here x we are putting as 1. So this term becomes 0, and this term will become 0, and as well as this term will become 0. Only this term it is going to remain. So here it will be this value will be equals to n factorial. That is what we have written, and this value we are going to get it as 2 power n. We are going to get. So now I will substitute this x value is equals 1 in this equation 6 also. So this one, that is Pn of x is equals to C of phi of x, whichever we have got. There we are going to substitute. Therefore, Pn of x1 is equals to C into phi of x at x is equals to 1. So this is C already we have, and phi of x at x is equals to 1, we have got this one. That is d power n, this one. Okay, at x is equals to 1, this is the equation which we have got. So therefore, in place of phi of x, we can write this 2, that is a C of d power n y by dx power n x at x is equals to 1. So this value is nothing but which is equals to 2 to the power of n factorial. So therefore, we have got Pn of 1 is equals to what we have got. C, this one we have got. Okay, sorry. From this is a equation which we have got. Pn of 1 is equals to C into 2 power n by n into n factorial. Sorry, C into 2 power n into n factorial we have got. Now, in order to get this constant, simply what we are doing is we will be taking into the denominator. So it will be Pn of 1 by 2 power n factorial. Okay, and already we have seen in one problem in the last class we have seen that is Pn of 1 value is equals to 1. So we are writing it is equals to 1. So what we have got, the constant is equals to 1 by 2 power n factorial. We have got this constant. Now, once you get this value of C, that is constant value we have got, so we will substitute in the equation this constant value. What is the equation 6 we have? Pn of x is equals to C into phi of x. So C value we have got it as this one. So therefore, in place of C, we will substitute this 1 by 2 power n factorial we will substitute. So therefore, here we have 1 by 2 power n factorial, and phi of x is d power n by dx power n. So therefore, we can write this Pn of x is equals to this as it is. We are writing this term as 1 by 2 power n factorial, and this d power n by y by dx power n. So we have assumed that y is equals to x square minus 1 whole to the power of n initially. That is the solution which we have been assumed. So therefore, in place of y, we are writing this one. In place of y, we are writing x square minus 1. We are writing x square minus 1 whole to the power of n. So this one, equation 8, whichever we have got, Pn of x is equals to 1 by 2 power n factorial into d power n by dx power n x square minus 1 whole to the power of n. This is the equation which we call it as a Rodrigues formula. We call it as a Rodrigues formula. We are going to be called. So with the help of this Rodrigues formula, we can get this different values of Pn of x. We can get like we can get P0 of x, P1 of x, P2 of x, and so on. So simply by substituting the n value like 0, 1, 2, 3, and so on, we can get these values. So P0 of 1. Okay. So P0 of 1 is nothing but n is equals to 0. We will substitute. So here it will be 1 by 2 power 0, 0 factorial. This total value we are going to get it as a 1. So P0 of x, we are going to create this one. So P1 of x is this value we can get. That is 1 by 2 power n means 2 power 1 factorial into this one d by dx of x square minus 1. So this d by dx of x square is 2x. So therefore 2 get cancels, x you are going to get. So similarly, we can get the P2 of x and P3 of x and so on. We can get P5 of x. We can get. So finally, we can conclude that Pn of x. That means n may be whatever maybe you are going to be have. So we can get Pn of x is equal to this is the equation we are going to get. That is Pn of x as this one we are going to get. That is summation of r is equal to 0 to n. N value may be 0, 1, 2, 3, whatever it may be. So we can get it as a minus 1 whole to the power of r into 2n minus 2r factorial by this you are going to get. And here, one thing we have to remember that if n value is equal to n by 2, okay, capital N value is equal to n by 2, this is for even, and capital N is equal to n minus 1 by 2, this is for odd. Okay. So this is the Rodrigues formula of Legendre's polynomial. So in each case, like if you go for Bessel's or Hermite's and all those things, you are going to have this Rodrigues formula. So this is a Rodrigues formula which we have. Pn of x is equal to 1 by 2 power n factorial, this one. So that is what we have proved here. Finally, Pn of x is equal to this one. Okay, this is what we have proved. So by if you want to know the values of different values, so this is a equation which we have like a P0 of x and Pn of x. Okay, so this is what we call it as a Recurrence formula for Legendre's polynomial we are going to be called, right? So similarly, we have orthogonal properties we have for Legendre's polynomial. So what are those orthogonal properties? We'll see here. Okay. So for first orthogonal property which we have is we have to show this is the equation that is uh, integration of -1 to +1. The limits we have Pm of x and Pn of x dx is equal to 0 for m is not equals to n. And we have this one that is integration of -1 to +1 limits Pn of x whole square dx is equal to 2 by 2 n plus 1. This is the one equation. Okay, so this these two equations whichever we have. Okay, so we can write using the Kronecker delta symbol. So Kronecker delta, so you have to remember, so this is the two conditions we have for Kronecker delta, that is delta mn is equal to 0 one condition if m is not equals to n, and delta mn is equals to 1 if m is equals to n. These are the two conditions you have to remember. Therefore, by using this Kronecker delta, this equation integration of -1 to +1 here, and in return it is -1 to +1, and Pm of x, Pn of x dx, which will be equals to 2 by 2n plus 1 into delta mn. Okay, delta mn value, if you see, its value depends upon the value of m and n. That means if m is equals to n, this delta mn becomes 1. If m is not equals to n, this will become 0. So this you have to remember. Okay, so we have to prove this the orthogonal properties of Legendre's differential equation. This is the one condition for m is not equals to n. This is another condition. This is another equation which we have. These are the three we have to prove with the help of vertical orthogonal properties we have to prove. So we know that already we have seen this is the Legendre's equation which we have. Okay, this is the Legendre's equation which we have in the last class. That is the Legendre's differential equation. This equation we can rearrange in this manner, that is d by dx of 1 minus x square into dy by dx plus n into n plus 1 into y is equal to 0. Means these two terms, the first two terms can be written as this one, d by dx of this value. Now if you see, this is the equation which we have. Now we'll take the Pn of x and Pm of x. These are the solutions of Legendre's equation 1. Okay, therefore here we'll write in one case Pn of x, in another case Pm of x. So it is d by dx of 1 minus x square, d by dx of Pn, because these Pn of x and Pm of x are solutions of Legendre's differential equation we have. So in place of y, we will write the Pm of x one case, another one Pm we are going to write. So if I write the Pn here, so this is the first equation we have. In place of y, we are putting Pn here. Okay, this one we have. And similarly here you see y, we are writing it as a Pn. So this is one equation. And another equation is we are writing simply Pm, okay, in place of y, because that is a solution of Legendre's equation. So we are writing in place of y Pm. So again here we are writing Pm, right? So now once you have been taken, these are the solutions, that is y is equals to Pm of x and Pn of x, and we are substituting in the Legendre's differential equation. So we are getting this two equations. Now what we are doing is we are multiplying this equation 2 by Pm and equation 3 by Pn. Okay, so we'll multiply this. Wait for 1-2 minutes. I'll start the class again. So wait for 2 minutes. I'll be back. Right. Sorry for the disturbance. So we'll start again. So we have substituted y is equals to these two, like as y is the solution, we have substituted Pn of x in one equation and Pm of x one in equation. So now what we'll do is we'll multiply this equation 2 by Pm, and equation 3 by Pn we are going to multiply. So here if you multiply this, 1 minute. Right. So here if you multiply with Pm is this equation 2. So Pm into d by dx of this entire equation we have. Right. Pm into d by dx of 1 minus x square into dPn by dpx. And we are subtracting this with the equation 3. So that is a Pn of d by dx 1 minus x square dPm by dx. Plus here, as we are subtracting these two terms here, these two terms becomes as this one. Okay. This term you are going to get. This is the term. Okay. So you see n into n plus 1 minus m into m plus 1. And here Pn is there, here Pm is there. So this you are going to get as Pn into Pm is equal to 0. So simply this equation 2 is multiplied with Pm and equation 3 is multiplied with Pn, and we have subtracted each. So here we have got this one equation. Now we have to integrate this equation between the limits -1 to +1. Okay. So we have to integrate this equation between the limits -1 to +1. So this is the integration of -1 to +1, limits -1 to +1. This equation that is we have. Okay, this term we have written here. Pm of df by dx, this one. And then the second term, again this one we taken the integration limits starting from -1 to +1. And this one we have taken, that is Pn of d by dx into 1 minus x square into dPm by dx into dx we have taken. And the last term, whichever we have here. Okay. So these are the constants. So we taken outside n minus m into n plus m plus 1. So if you rearrange these equations, we are going to get these. Okay. Rearranging means simply we multiply and write. Okay. So here if you multiply with n into n square plus n, you are going to get here minus m square plus minus m you are going to get. That is what we have written here. Simply, no problem. You can check this. And the integration limits are from -1 to +1 and Pm of dx is equal to 0. Now, after getting this, okay, so we will integrate this equation in between the limits -1 to +1. Initial first term is Pm of this one. Okay, so this one d by dx of 1 minus x square is. So here we are going to get this one. 1 minus x square we have taken out, so dPn by dx integrated. And we have substituted the limits -1 to +1 here. And this one we are writing as it is. Okay. The second term we are writing as this. Only the thing is we have taken dPm by dx outside. This one we have taken outside. Okay. And another term here we have Pn of 1 minus x square into dPm by dx. This one. Okay. So this is also limits are from -1 to +1. So plus this integration between the limits +1 to -1, we have this entire second term, which we have this one we are writing here. So simply, if you substitute the limits -1 to +1, this term is going to be get it as a 0, and these terms are going to be remains. Okay, so this is the one term which is going to remain. This is the second term, and this is the third term. These two terms are going to be become 0, right? So now, in these, whatever the terms which we have left over, so we'll take n minus m into n plus m plus 1 outside this one. So integration of Pn of x, Pm of x dx, this one. Okay. So this value also equals to 0. Now we will take the condition, that is if n is not equals to m. If n is not equals to m, this is the equation which we are going to get. So from integration of -1 to +1, Pn of x, Pm of x dx is equal to 0. This is one orthogonal property which we have. So the first orthogonal property. You see what is the first orthogonal property we have is this one. Integration of -1 to +1, Pm of x, Pn of x dx is equal to 0. For m is not equal to n. So that is the reason why we have taken the condition if m is not equals to n, right? Then after, in order to prove the second one, so what is the second orthogonal property we have is this one. Integration of this -1 to +1 Pn of x square dx is equal to this. We have to prove 2 by 2n plus 2. So in order to prove that, we will be considering the generating function of Legendre's polynomial. So this is the generating function of the Legendre's polynomial for z power n and for z power m, right? So for both Pn of x and Pm of x, these are the two generating functions of Legendre's polynomial. Now we'll multiply these equations. Okay. So if you multiply these equations, so it is having 1 minus 2xz plus z whole square, sorry, z square whole to the power of minus half. This is also minus half. Minus half plus minus half, you are going to get it as minus 1 you are going to get. Okay. So if you multiply these two terms, minus half into minus half, you are going to get it as b plus half, no? Okay. Minus 1 you are going to get. And on the RHS, whichever we have, this term and this term, here we are writing summation of 0 to m is equal to 0 to infinite. This one, z power m Pm of x. Another one is summation of 0 to infinite, z power n Pn of x. These two. So these two will take here. Summation of m is equal to 0 to infinite, and simply we are writing this one, z power m into z power n. This one we are writing. Now the condition is we have to take m is equal to n. Okay, if m is equal to n. So if m is equal to n means this entire summation for m is equal to 0 to infinite, for n is equal to 0 to infinite becomes as this. That is summation of n is equal to 0 to infinite, it becomes. And here m is equal to n. We will write m is equal to n. So z power n, another z power n. So it becomes z power 2n. And this Pn of x and Pn of x whole square it becomes. So now we will be integrating this equation. Okay, integrating this equation, entire equation, both sides with respect to x between the limits again -1 to +1. So we have written integration of -1 to +1, 1 minus 2xz plus z square whole to the power of -1 into dx, which is equal to again summation of n is equal to 0 to infinite, z power 2n we taken outside, and integration between the limits -1 to +1 Pn of x whole square we have. Therefore, the integration of this will be -1 by 2z and log. This is actually in the order of 1 by x. Integration of 1 by x is log x. So log x is this one. In place of x, we have 1 minus 2xz plus z square. Log of 1 minus 2xz plus z square. And the limits applied are from -1 to +1. And inside, if you do the different integration, we are going to get it as a -1 by 2z. On the RHS, again, we kept it as it is, same as it is. N is equal to 0 to infinite, z power n -1 to +1, and Pn of x whole square, sorry, dx, we will write as this. Now here, this one, whichever we have, this one, log of this one, okay. We can write it as a log 1 minus z whole square minus log 1 plus z whole square, we can write. 1 minute. Sorry for this offense. Okay. So here, this log 1 minus 2xz plus z square, we can write like in this form, we can write. Okay, log a minus log b, actually, we can write in this form. So if you expand this 1 minus z whole square, and if you expand this 1 plus z whole square, if you do this term, you are going to get here. So RHS we will write as it is. This one as it is, we are going to write. Now, this log 1 minus z whole square, log a square minus log this one, log a square minus log b square means in terms, we have. So we can write this as this one we can write. Okay. So again, we write as it is in the RHS. And now we'll expand this here, log A plus B minus log A minus B. So in this form, we can expand like z minus z squared by 2 plus z cubed by 3. This we can expand. So we can write this term. Now we will combine these two terms so that we'll get this one. Because z, this is z cubed by 3 plus z means you see here, if you multiply this minus into minus plus, you are going to get here plus z, and similarly here plus z squared by 2 you are going to get, and plus z cubed by 3 you are going to get, and so on you are going to get. So if you see here minus into minus plus, this z squared by 2 term, this is minus z squared by 2 term is going to be get cancels. And similarly in this, whatever the term which we are going to get the even multiples of z, that is z power 4, next term which we are going to get here is minus z power 4 by 4 you are going to get. Here also we have this z square by 2. Next term also we are going to get as a plus z square z power 4 by 4. So the term also going to get cancels. So if you see here, what we remain only the odd multiples, means not odd multiples, the squares whichever we have, like z power 1, only odd squares we have, z power 1, z cubed by 3, z power 5 by 5, and z power 7 by 7. And we can generalize the term as z power 2n plus 1 by 2n plus 1. So n value can take like a 1 if you put here. So it will be z power 3 by 3 factorial. So if you put n value as 0, it will be z power 1 by 1. So like that you are going to get. So here we will write this z and this z, it becomes 2z. This z cubed by 3, z cubed by 3, it becomes 2z cubed by 3. So we taken outside 2. Right. So on the RHS, we have written same as it is. Now, here, if you multiply, if you divide with this z, so the inside whatever we have, we will get as this z cancels 1 z cancels, z square by 3, z power 4, like that you are going to. So now we will equate the coefficients of z power n 2n on both sides, z power 2n. So if we equate the coefficients of z power 2n, so the coefficient of z power 2n, whichever we have, is this one. That is this entire equation. That is integration of -1 to +1 Pn of x whole square dx. So that is what we have here. And the LHS, the coefficient of z power 2n we have to take. So if you take the coefficient of z power 2n, it will be 1 by 2n plus 1, and 2 here it is there, 2 into 1 by 2n plus 1. So it will be 2 by 2n plus 1 we have. So now we have got these equations. Okay. So this is equation 5 we have got. Now if you combine these equations 4 and 5, fourth equation is here we have. Okay, this equation. This is the first orthogonal property which we have been proved. If n is not equals to m, this one. And this is the second orthogonal property which we have proved. So if we combine these two, so we have in the fourth equation what we have, this entire, if m is not equals to n, this total will become 0. So and in the equation 5 you see this value is equals to n plus 1. So integration of by combining these two, this equation and previous equation, here we have Pn of x square, there we have Pn of x. So we'll get it as integration of -1 to +1 Pn of x. In that term, we have Pm of x into dx is equals to this 2 by 2n plus 1. Here we have written the canonical delta mn we have written. Okay, delta mn we have written. So that is the we got delta mn. And again, delta mn value is equals to 1 here, because m is equals to n. If you take 1, you are going to get. So this is the one orthogonal property we have. Okay, so 3 orthogonal properties. You see, the first one which we have taken, this one we have proved, and the second one we have proved this one. By combining these two, we have proved this one. Okay, third orthogonal properties, by combination of these two, we are going to get. So this is the these are the orthogonal properties of Legendre's differential equation. Similarly, we have recurrence formula for Pn of x. Okay, we have recurrence formula. So this is what we have to prove. We have some recurrence formulas. So nPn is equals to this we have to prove here. Okay. So in order to prove this, we will take the generating function. This is the generating function. Now we will differentiate this equation with respect to 2z. So if you differentiate with respect to 2z, x to the power of n is differentiation is nx to the power of n minus 1. So that is minus 1, or minus half, and this term to the power of minus 3 by 2. And the differentiation of this, we are going to get it as a minus 2x plus 2z. And here, z power n differentiation is nz power n minus 1. So if you rearrange, we'll get this. Get this equation here. Okay. Once after that, we'll multiply this equation with respect with 1 minus 2xz plus z square. We are going to multiply. So we have multiplied on all LHS, and similarly on the RHS also we have multiplied this. Okay. So that here you see we get x minus z, and this term whichever we have. So this term 1 minus 2xz plus z square whole to the power minus m. Already we have written this, which is equal to this one. The summation of n is equal to 0 to infinite z power n pn of x. This already we have proved. This is equal to this. So in place of this, we are writing this one here, right? Therefore, on the RHS we are writing as this initial term 1 minus 2xz plus z square, and here summation of n is equal to 0 to infinite, same as this we are writing. Now here, what we are doing is we will equate the coefficients of z power n minus 1, not z power n, z power n minus 1. So if we equate the z power n minus 1, so what we have to write is simply in place of n, we have to write n minus 1 here. In place of n minus 1, we have to write. So what is the coefficient of z power n minus 1 we have is, here we have this pn minus 1, we are writing here. Okay. Base of n, we have to write n minus 1. So therefore, this becomes x into this value pn of minus 1 and minus pn minus 2 you are going to get. And the RHS, the right hand side whichever we have is this. It's npn minus 2x, pn minus 1, pn minus 1 plus n minus 2 pn minus 2. Okay. So simply we expand this pn of x. Right. So therefore, finally we'll get npn. This one is equals to 2n minus 1 of x pn minus 1 minus n minus 1 pn minus 1. This is what we call it as a first recurrence formula we are going to talk. Okay. So once if you practice, you'll get this one. Okay. Similarly, we have another formulas of generating function. With the help of generating function, we are going to be get this one. This also we have to show recurrence formula. Okay, this is one more we have. So just if you see your if you have your material, all these entire notes will be available with you. So each and everything, if you want to continuously tell, we won't complete the syllabus because we have only 9 classes. Within the 9 classes, we have to complete. So this is the one more recurrence formula we have. You go through this. Okay. In your notes also you have this one, right? So this is the recurrence formula we have. So this is about Legendre's differential equations. So we have seen the Legendre's differential equation we have seen, and for the Legendre's differential equation we have seen the Recurrence formula we have seen, and also orthogonal properties we have seen. Okay. So this is about the Legendre's differential equations. Right. So Legendre's differential equation is over. So after this, we have like a Bessel's differential equation we have. Okay. Bessel's differential equation. Yes. We have Bessel's differential equation we have. So for this Bessel's differential equation, before this Bessel's differential equation, we should go through these gamma functions as well as the beta functions. So if you are familiar with this what we call gamma and beta functions, then only it is able to understand what we call Bessel's differential equation. Otherwise, because we'll be using these Bessel's gamma and beta functions in the Bessel's differential equation. So that is the reason why we should know about gamma and beta functions also. So now what I'll do is I'll go with gamma and beta functions, and then after we'll go through this what we call Bessel's differential equation. So for that purpose, we'll solve first gamma as well as the beta functions. Now I'll share this gamma function, then we'll start with gamma function. Okay, 1 minute. So this is the gamma function. You have in your what we call in your material also gamma function is there. So you go through this gamma function. 1 minute. Wait for 1 minute. So if you have your material with you, you can see. If you see, once you go through your material, so which we have Bessel's function. So Bessel's function we have. So in the Bessel function, if you see, you get the two cases, case 1, case 2. One is for k is equals to n, you are going to get. Another one for k is equals to minus n, you are going to get. So in the case of the k is equals to n, if you want to prove, we have to know this gamma function. Otherwise, we cannot. So that is the reason why just simply we'll reveal this gamma function. This reveal gamma function, then we'll go to the Bessel's differential equation. So if you see here, actually the gamma function, which can be denoted as this gamma of n. Okay. So which gamma n can be written as integration of 0 to infinite. Okay, this one. Integration of limits between 0 to infinite x to the power of n minus 1 a to the power of minus x dx. Okay. So this is the gamma function we are going to become. So with the help of these gamma functions, we have certain values we have, like gamma of n plus 1 is equals to n gamma n we can write, and similarly gamma of n plus 1 is equals to factorial we can write. Gamma of 1 is equals to 1 we can write. These you should know because we will be using these in the Bessel's differential equations. So similarly gamma of 0 is equals to infinite. This is the one we can write. And similarly, gamma of minus n is equals to alpha square we can write. This is for a positive integer. Similarly, gamma of minus half is equals to, we can write it as a root pi we can write here. Okay. So gamma function is, we can call it as, sometimes call it as a factorial. Okay. So if you see first one, that is a gamma function of n plus 1 is equals to n root n. So we can prove with the help of this one, because what we have, the definition gamma function is equals to this one we have. Okay, that is gamma of n is equals to integration of 0 to infinite x to the power of n minus 1 e to the power of minus x dx. This is what we have gamma function. Okay, so that gamma function they have been taken, and we are writing this gamma of n plus 1. So gamma of n plus 1 is, in place of n, we will write this n plus 1. So this integration of 0 to infinite, in place of n, we are writing n plus 1 here. Okay. And e to the power of minus 1. So now this one we can write it as integration of 0 to infinite x to the power of n e to the power of minus x. We can write, because plus 1 minus 1 get cancels here. So it will remain with x to the power of n e to the power of minus x. Now again we will be integrating this by parts, that is integration of uv dv. Okay, so this one we have integration of uv dv. This is a formula. Based on this, we will integrate this one, so that we'll get this x to the power of n e to the power of minus x. The limits are from 0 to infinite, plus integration of 0 to infinite n x to the power of n minus 1 e to the power of minus x. That is integration of the differentiation of x to the power of n is nothing but nx to the power of n minus 1. So now if you take this, here we are written minus x to the power of n e to the power of minus x 0 to infinite plus, and this n will be taken outside. So n, and the limits are from 0 to infinite x to the power of n minus 1 e to the power of minus x dx. We have to take. And here, if you substitute the what we call this limits 0 to infinite in this equation, we'll get it as equals to 0, and this is n we have, this n, and this value integration of 0 to infinite x to the power of n minus 1 e to the power of minus x dx. So this is equal to root n, because this is according to this. Okay, this is what we have gamma function, no, integration of 0 to infinite x to the power of n minus 1 e to the power of minus x. So that is what we have got, integration of 0 to infinite x to the power of n minus 1 e to the power of minus x as gamma n we have written. Therefore, root of gamma n plus 1 is equal to n root n we have proved. Okay. Similarly, we can prove this also. That is root gamma of n minus n is equal to n minus 2 root of n minus 2 we have. Okay, this one also we can write. So this one, and similarly we have this uh, gamma of 1 is equal to 1. This also we can prove. So this is the gamma function we have. So therefore, gamma of 1 is equal to, in place of n we are writing 1, so it will be x to the power of 1 minus 1 x to the power of 0 e to the power of minus x, and the gamma of 1 is equals to integration of 0 to infinite e to the power of minus x, because x to the power of 0 is equals to 1. So now the integration of e to the power of minus x is minus e to the power of minus x. The limits are from 0 to infinite. So if you substitute in place of x infinite and 0, we will get it as a 1 we are going to get. So therefore, gamma function of 1 is equals to 1. This is one we have. Next one, we can have this one. That is, we have to show gamma function of n plus 1 is equals to n factorial. We have to show. So for which we have n values are starting from 1, 2, 3, and so on. Okay. Therefore, we know that this already gamma function of n plus 1 is equals to n root n. Already we have this. Okay. Therefore, n, this one we can write it as n into n minus 1 root of n minus 1 we can write this equation. Okay. Therefore, n into n minus 1, and this root n minus 1 can be written as n minus 2 into root of n minus 2, because n what we have written, n into n minus 1 we have written. So the n into n minus 1 we have. Therefore, root n minus 1 can be written as this one, n minus 2 into root of n minus 2 we can write. So if you continuously write, you'll get this equation as this one, n into n minus 1 into n minus 2 into n minus 3 and so on up to you are going to get. So n factorial we can write. And ఇక్కడ n minus 1, n minus 2 ఉంటే 2 factorial we have to take. Suppose if you continue to n terms, we can write it as n factorial. So therefore, this is the proof of the gamma function of n plus 1 is equal to this we have. Right. Similarly, we have some problems. We go through these problems and share. Okay. So these are the basing upon gamma functions only. These are the problems we have. Okay. So this is about the gamma function. Then we'll move to Bessel's differential equation. So in the gamma functions, if you have any doubt, you can ask me later. So you should know about these, because these are the very important, the gamma function. So these we are going to be used. Means directly, if you are getting gamma function of n plus 1, we can write this one. So these we are going to use. So this is about gamma functions, right? Similarly, you have beta functions also. Beta functions, wherever we are going to be get, we will see that. Next, we'll move to Bessel's differential equation. Okay, BDE, that is Bessel's differential equation. We are going to be more. I'll share this Bessel's differential equations. I'll start.
Sandeep. Sandeep. బిల్లు ఎక్కించుకోరా ఎడగొట్టిస్తావా పెట్రోల్ అది కొట్టి సందీప్ అక్కడ ఎందుకు ఇక్కడ కొట్టిస్తే ఏమవుతుంది ఇక్కడ కొట్టిస్తే ఏమైంది ఇక్కడ కొట్టించి బిల్లు ఇచ్చేస్తా సరే సరేనా ఆ హెల్మెట్ మంచి పెట్టుకో ఆ హెల్మెట్ ఎంత ఉంది నీ ముఖానికి ఇంత అంత ఉంది Mute yourself now. Very good.
Okay. So all of you, do you have your material with you so that we'll start the Bessel's differential equation? Do you have or not mathematical physics material with you? Any one of you should respond.
Yes, sir.
Okay, just because first we'll see the Bessel's differential equation, then we'll move to general solution and all those things. So 1 minute, I'll get the So this Bessel's differential equation is also similar to the procedure whatever we are going to be follow. In the case of the Legendre's differential equation, whatever we have similar we have to follow for Bessel's as well as the Hermite's or some other thing. So we will see here Bessel's just you go through your material so that I'll explain. And then after I'll share the notes of this generating functions of Jn of x. We have recurrence formulas and as well as the what we call orthogonal properties. So if you have your material, just you go through. Why? Because uh, it is unable to write on board. So here we have differential equation for Bessel's as x square into d square y by dx square plus x into dy by dx plus x square minus n square into y is equals to 0. 1 minute, otherwise I'll share 1 minute.
Sir, class completed. Hello. సార్ క్లాస్ ఉందా సార్? హలో